Welcome to the core problem of econometrics. Basic statistics is often satisfied with finding correlations, noticing that two variables tend to move together. But econometrics demands something harder. Our goal is to isolate true, undeniable causality from messy observational data. To prove causality, we rely on a principle called Ceteris Paribus. It's a Latin phrase meaning other things being equal. If we want to measure the exact effect of one variable on another, we have to hold every other relevant factor perfectly constant. The mathematical framework for this goal is the simple linear regression model. We start with y, the dependent variable we are trying to explain, and x, the single explanatory variable we are tracking. The most important piece of this equation is beta 1. This is the slope parameter. It represents the exact ceteris paribus effect we are desperately trying to measure. How much $y changes when x increases by exactly 1 unit, assuming nothing else shifts. But we have an antagonist in this model, the letter u. This is the error term, sometimes called the disturbance. In a simple regression, u acts as a massive container. It holds every single unobserved factor in the universe that affects y, but isn't explicitly measured in our single x variable. Let's ground this in a classic labor economics example. Suppose we want to explain a worker's hourly wage, our y, based purely on their years of formal education, our x. If education is the only thing we measure, the error term u becomes incredibly crowded. It now contains the worker's innate ability, their years of on-the-job experience, their work ethic, their professional network, everything that influences a paycheck but isn't a diploma. This chart shows the reality of observational data. Look specifically at the vertical slice of people with exactly 12 years of education, high school graduates. Their wages are scattered all over the map, from minimum wage up to high-earning salaries. Because every person in this stack has the exact same value for X, education cannot explain the difference in their pay. This vertical variance is caused entirely by the unobserved variables hiding inside U. This leaves us with a severe mathematical problem. It is impossible to calculate the true ceteris paribus effect of education on wages without imposing strict mathematical restrictions on how the unobservable u behaves and relates to our known variable, x. We start with a baseline assumption about the error term. Its average value across the entire population is 0, or E of u equals 0. This normalizes our unobserved factors, but it only anchors the intercept of our equation. It doesn't solve our causality problem. To actually isolate the effect of x, we need a much stronger requirement. The average value of the unobserved factors must not change depending on the value of x. Mathematically, the expected value of u given x must equal the expected value of u overall. Because we already set the overall average to 0, this condenses into our definitive rule, the zero conditional mean assumption, E of u given x equals 0. Applied to our wage example, this dictates that the average innate ability, or experience, or work ethic, must be identical across all education levels. You can immediately see how fragile this is. If naturally high-ability people systematically choose to stay in school longer, then the average ability for college graduates will be higher. If that happens, the assumption fails entirely, and our simple regression model falls apart. This chart shows the theoretical result if the zero conditional mean assumption holds. It creates the population regression function. By forcing the unobservable errors to average out to 0 at every point along the x-axis, the expected value of y becomes a strictly linear function of x. For every 1 unit increase in x, the expected value of y moves by exactly beta 1. Notice the distributions plotted here. For any given x, actual outcomes of y spread out in a normal distribution centered precisely around that regression line. But there's a catch. This population regression function represents an absolute truth we can never actually observe. We leave the infinite theoretical population behind. Now we are dealing with a tangible, finite scatterplot of real sample data collected from the field. This chart illustrates our mechanical estimation. The physical gap between our line's prediction and the actual data point is the sample residual. Unlike the invisible population error u, this sample residual, u hat, is a physical measurement of how badly our line missed. To find the optimal line, we use a mathematical bridge called the method of moments. The core logic of this method is substitution. We take the calculable sample residuals we can see, and we force them to obey the exact same rules we assumed for the theoretical population errors we can't see. Recall that in the population, the error term has a mean of 0 and it has 0 covariance with x. To match these facts, we create two algebraic equations that force our sample residuals to sum to 0 and to have 0 correlation with our x variable. These sample equations act as mathematical constraints, dictating how our estimated line must behave. By solving these two equations for the unknown variables, we isolate the exact formulas for our estimators, the estimated intercept and the estimated slope. If you look at the denominator of the formula for the slope estimator, it exposes a fundamental mechanical requirement. To calculate the slope, there must be mathematical variation in the x variable within our sample. This chart demonstrates a sample lacking variation in x, like surveying only people with exactly 12 years of education. The differences from the mean equal 0, destroying the denominator. The math breaks down. You cannot fit a single line through a vertical stack of dots. Assuming our data does vary, solving these sample equations yields the ordinary least squares, or OLS, estimators. OLS is the unique mathematical solution that guarantees the sum of the squared residuals across the entire sample is as small as theoretically possible. Let's apply the OLS mechanism to a real dataset. We are going to analyze the compensation of corporate chief executive officers to see if firm performance predicts their pay. Our dependent variable, Y, is the CEO's annual salary, measured in thousands of dollars. The explanatory variable, X, is the firm's return on equity, or ROE. ROE is a metric that measures net income as a percentage of common stock. Keep in mind that a CEO's salary is dictated by countless unobserved factors, such as prior experience, their negotiation leverage, and board connections, all of which are currently hiding in the error term. This chart shows the final sample regression function calculated by OLS. The solid line is the mathematical best fit. Notice the hat over salary. These are sample-derived predicted values, not absolute truths. The slope directly predicts a 1-point ROE increase raises salary by $18,500. The intercept tells us the baseline. It represents the predicted salary, $963,191 for a CEO whose firm's return on equity is exactly 0. But we have to understand the limitation of this output. The sample regression function predicts the conditional mean for the group. It does not guarantee the exact salary for any single individual data point, because the error term still exists for every single CEO. Finally, look at the dashed line on this chart. That represents the unknown population regression function, the absolute truth. Notice how it deviates slightly from our solid sample line. Our OLS estimate is close, but it relies entirely on this specific sample slice. OLS perfectly executes the math to draw the best-fitting line for any given sample. But the economic validity of that line, whether it proves a true causal relationship between a company's profits and a CEO's paycheck, depends entirely on whether the 0 conditional mean assumption holds true in the messy, unobservable real world.